myself. Okay. Well, we will find out when we upload to YouTube. You've stopped screen sharing. All right.
You get your YouTube and stop screen sharing.
I see. Okay. Pause. Stop recording. Audio's on. Good. Okay. I think the iPad went to sleep, and then all right. Sorry. We'll come back to that. Okay. I was on such a roll. Okay. So we will find extremely important results and insights from the mathematics of Lie groups and Lie algebras, and then even more so the representation theory of Lie groups and Lie algebras. And if you want to go very deep, we will touch on this, but I don't think we'll go into any real detail, but I can point you to resources if you're really interested in this. In the topology of the group manifolds of the symmetries that our systems obey, and in particular, the algebraic topology of those groups, whether they are simply connected, and if they're not simply connected, what their fundamental group is. So that, to me, is the royal road to symmetries in quantum mechanics, the royal road to what the particle content of your theory can be, and the royal road in terms of deep mathematical connections to really fun, interesting mathematics and physical consequences. Cool. Good. Any further questions on stakes as raised before we continue? Great. Let me start sharing the screen again, hopefully. Good. Great. All right, let's go to symmetries in quantum mechanics. So perhaps to set the stage, I've been saying this before, but you know, we're going to talk about symmetry transformations. The canonical example in non-relativistic quantum mechanics is rotations. So perhaps as we continue, keep the idea of rotations in the back of your mind as a canonical example for what we're doing. But as we know from Einstein, time and space are on equal footing. And so in some sense, spatial translations, time translations, those are also going to be symmetries that we would like to understand. So that's why I'm going into this. It'll be a fairly deep dive for probably a few lectures on symmetries in quantum mechanics before we get to the time-dependent Schrödinger equation, making a more deep dive into that fourth postulate of quantum mechanics. Okay. All right. So a symmetry transformation is a change in our point of view that does not change the results of possible experiments. So hopefully right now your brain is immediately firing, thinking about, conservation of inner products, unitary operators, rays being insensitive to changes of normalization and phase. Hopefully that's all popping in your head. All right. Super. All right. So if an observer called the observer O, a bit of not an abusive notation, but a running out of letters. So it's not an O hat observable, which is represented by an operator on a Hilbert space, but just an observer O, sees a system in a state represented by array R, or R1, R2, so on and so forth, then an equivalent observer, say O prime, will see the system in a state represented, sorry, bit of feedback there. So we'll see the system in a state represented by array, call it R prime, or R1 prime, R2 prime, so on and so forth. However, so while the representation may be different, we must have something. We must have that the observers agree on the results or agree on the probabilities for the outcomes of experiments. So we must have the probability of, say, the state collapsing from R down to, say, Rn must be equal to the probability of the same state, but as seen by the other observer, collapsing down to the same measured state, again, in the way that the O prime observer conceptualizes or mathematically describes the system. So, for example, if I have an experiment and I measure that the electron is spin up in my coordinate system in the z direction, if I have somebody, say Rachel, whose z is in this direction, then Rachel will say, oh, the electron was measured to be spin up in the x direction. And we just know that your x direction is my z direction. And we agree that the measurement was the same. Good. All right. Now, by a theorem from Wigner, called Wigner's theorem, if you want to Wikipedia it, for any such transformation of rays, where R is going to R prime, we may define an operator U hat on the Hilbert space H such that if the ket psi is in array R sub psi, then the ket defined by this unitary operator acting on the ket psi is in the ray R prime of, say, psi prime. well, it's R prime of, let's call it R prime of psi, right? Right, so if I have a symmetry transformation, then I have an operator where the state that's representing the system by observer O is taken into a state that's representing the same system by the observer O prime. That's what a symmetry transformation does. And that's the mathematics that is doing that for us, is this operator U on the Hilbert space. This operator exists. Further, with either one, U hat is unitary and linear, which is to say that U phi U psi is equal to phi U dagger U psi is equal to phi U inverse U psi, which is phi, the identity, psi, I'm being super pedantic here, which is phi psi. This is precisely that statement that the probabilities are not changing from the way that observer O is described in the system and the way that the observer O prime is described in the system. And second, we have that, so this is the unitariness. And then the linearity says that, excuse me, the unitary operator acting on some linear combination of states is the linear combination of the operator acting on the states. So that's linear and unitary. Those are just definitions of what unitary means and what linearity means in this context. Good questions? No questions, great. So possibility one is that U is unitary and linear. Possibility two is that U is anti-unitary and anti-linear. What do I mean by that? So I mean that, let's call it in fact A to differentiate. And so if I have A on phi overlap A with psi, this is equal to the complex conjugate of psi, I'm sorry, phi with psi. Right, so that's the opposite of what we had up above. So we had that U phi overlap with U psi, gives me phi with psi overlap. Now we have A phi overlap with A psi, gives me rather the overlap of psi with phi. Subtle difference. Okay, so that's anti-unitary. And then anti-linear says that this A operator acting on alpha phi plus beta psi, this is equal to the complex conjugate of alpha phi plus the complex conjugate of beta psi. Defining the Hermitian conjugate of an antilinear operator as, say, phi A hat dagger psi is defined as A phi psi complex conjugate, which is psi a phi, then the representation of a symmetry transformation on a complex vector space or on a Hilbert space say U hat must satisfy U hat dagger equals U hat inverse, our usual definition of unitary. So again, I would wager to say that, or I would certainly say from my own experience that this was not communicated to me in any of my undergraduate or graduate quantum mechanics courses, but I think it's of fundamental importance because we would like to describe, for example, rotation. So we'd like to understand how to do that. I would say further before I open the floor for questions, which I welcome, that the possibility of anti-unitary and anti-linearity is only ever going to come up with the discrete symmetry of time reversal, which we're not going to cover for a variety of reasons. Mostly just time. We just don't have enough time to talk about it. So if part of your, if you might have some anxiety related to anti-unitary and anti-linearity, you're right to be anxious, but don't worry about it. We're not going to touch on it in any significant way. Yes.
Just to clarify, when you describe the anti-linearity, the A hat is supposed to be before the.
Oh gosh, I completely got rid of the A. Sorry.
That's fine. I figured it was.
Yeah. Great. Thank you. I got too excited to get to the end. Yeah. Great. Thank you. Other questions? Yes.
Can you just move down this?
Sorry, this way? Okay, great. You're welcome. No, so the Hilbert space H, so but the representation is going to be the U. So maybe I could say the representation U. Oops, I lost the hat, but we can put that back. Yeah, great. Good. Any last questions before we continue on? Where I hope that as we continue, things will become, familiar is too strong of a word, but you'll become more comfortable with these ideas. Okay, great. Yeah.
With the two different the operating U, so it can either be unitary and linear or anti-unitary and anti-linear, but either way, it's still like a symmetric transformation. I'm just confused with the.
So when you say, is it still a symmetric transformation, do you mean that either way, U is effecting the symmetry transformation on our Hilbert space? Yes. And the thing that's so incredibly powerful about this is that this is exceptionally limiting. So this is coming sort of from the philosophy of, or what I interpret as Weinberg's philosophy of understanding the universe and the profound ways in which the types of physics that we can see are limited drastically purely by the assumption, in general, quantum mechanics and special relativity, but in this class, we're mainly going to focus on the assumptions of quantum mechanics. And by assumptions of quantum mechanics, I mean those four postulates. So those four, I would say, fairly simple, fairly succinct postulates, which, okay, there's a lot of mathematical background that we're going through to understand those, severely limit the types of things that we can see in the world around us. And ultimately, the types of things we do see around us fall precisely into the categories of things that can be seen based on the assumption of quantum mechanics. So that's some really profound realization and understanding of the natural world that I want to communicate to you and have you have an appreciation of. As a bit of foreshadowing, if you are probably at this point sort of comfortable in the sense that you've just done many times, you have categorized the unitary irreducible representations of rotation group in 3 dimensions, and you see that you get spin 0, spin 1/2, spin 1, so on and so forth. And you're like, okay, cool, that's great. But if you do the same categorization of the unitary irreducible parenthetically projective representations, we'll get to that in detail later, for rotations in only 2 dimensions, then you get that the intrinsic angular momentum of an object can have any real number value, not necessarily integer or half integer. So if physics is restricted to just a 2-dimensional plane, you can have objects that are not bosons or fermions. They're known as anyons. And they smoothly interpolate between the statistics of bosons and fermions. But because the world that we generally interact with has 3 spatial dimensions, the types of particles are severely limited in the types of intrinsic angular momentum they have. I find that profoundly interesting. Yeah. Yes.
Could you write down in a similar fashion the emission conjugate of the just right next to the emission conjugate of an anti-union, just so I can see the difference?
I don't yet see your question. So here's the linearity for the unitary and linear operator. Here is the anti-linearity for the anti-linear anti-unitary operator. Do you want to see what happens when this operator acts on a bra?
No. When you define the emission,
Yes, here.
oh, is that it?
Great.
Yeah, thank you.
Well, yes. Yes, absolutely. So this is what we usually think of as unitary. What we're doing here is we're now sort of playing around with the math for anti-unitary operators in such a way that this statement will still hold even for anti-unitary operators. Correct. Yes, good. Good, thank you. Final call for questions. And if there are, yeah, please ask.
Sorry.
No, this is good.
I'm confused now. Like, you know what you think, yeah.
I was just talking about like docket.
And
Then the first thing is true.
Yeah, in number 1, yeah, so you know when you say really example, you
we should define a unitary operator that it preserves the inner product with us. We shouldn't define it by whether the dagger is.
So you said it's unitary. If it's unitary, then that goes.
What's the first one? Oh, yes.
Let me propose, just because I think there are going to be some minus signs that I'll have to be careful with. Let's park this until the next time. I think I understand your question. Just let me sort of get to that very briefly then. Good. You're welcome. Okay. Good. Are there any more questions? And it is okay. Because this is where the learning happens. And as I said, the priority here is to learn. Ben and I had a nice conversation yesterday, which was, is our goal to do fast and superficial or sort of less material and deeper? And I think the idea is to go deeper. More is better also. So yeah, but okay, great. Very good. All right, so for any symmetry transformation, there's a trivial identity transformation. In which the observer O prime is O. In this case, U is just the identity. One is unitary and linear. So any symmetry transformation that can be continuously connected to the identity must be represented by a unitary and linear operator. U. So, for example, rotations, translations, but not necessarily reflections in time or space. It turns out that the parity operator is unitary and linear, but it's not required to be necessarily from this first principles mathematics consideration. All right. So while we're on the subject of infinitesmal transformations, near the identity, must have the form. So our operator must be just the identity plus I, and then some set of real parameters that are small in some linear combination of some operators T plus higher orders in epsilon. Where these epsilon A1s through AN are infinitesimal real parameters. Since this U is unitary, U dagger equals U inverse, we must have that the T hat daggers must be equal to T hats. I.e., we'll find that the operators that generate symmetry transformations at least symmetry transformations that are continuously connected to the identity are Hermitian. And are therefore candidates for observables. The great Weinberg himself, he has a statement, which is that most, perhaps all, observables arise from symmetry transformations. Okay, any questions on this? So we're slightly over time, but just in preparation for Thursday, just so that we're all on the same page, the next step is to define what a group is. So I just want to write down the definition of a group, or we can cut it and just say it's on you to look up what the definition of a group is on Wikipedia. I would propose I write it down quickly. Good. So we'll call the definition of a group. So a group G, or rather a group is a set G, set of elements G, along with an operation. Call it little circle, which takes two elements of G and spits back another element of G. So the group is both the set of elements and the operation that satisfies one closure, which is to say that for all elements A and B in our set G, if you perform the operation on those two set elements, you end up with some element still of the set G. 2, associativity. So this is that for any 3 elements A, B, and C of our set G, then if we act A on B acting on C, then that's the same thing as A acting on B, which itself then acts on C. There's an identity. And that says that there exists some element of the group such that for any element of the group G, then the identity acting on that element gives the element back again. One can prove that the left identity is the same thing as the right identity. and that inverses exist. So for all elements of our set G or our group G, there exists some object that we call A inverse, which is also in the group G, such that A inverse acting on A gives back the identity. And one can prove that this left inverse is equal to a right inverse. The idea of groups is to abstract away from our idea of the integers under addition. So what are the salient properties of integers under addition? And the claim is that the salient properties are closure, associativity, there's the existence of identity, and existence of inverses. And that there are plenty of other sets with other operations that also satisfy these properties. So for example, the rational numbers under multiplication, or n by n matrices with real entries and non-zero determinant under matrix multiplication. And so whenever you've identified a set of elements with an operation that satisfy the properties of groups, you know a lot of things. For example, that the identity is unique, the left identity is the same as the right identity, left inverse is the same as right inverses, so on and so forth. And what we'll go through in more detail the next time is that we want to prove that symmetry transformations form a group. And that's going to have some important consequences, as I alluded to earlier. Before I wrap up, just take a moment. Any last questions? Amazing.